Displacement current. Consider a circuit containing a capacitor and a battery. When the battery is switched on, let a current I flow through the circuit. We know current produces magnetic field. According to Ampere's circular law, the line integral of magnetic field around any closed path due to a current carrying conductor is equal to mu 0 times the current enclosed. Let us take an Amperian loop. Now, when you apply Ampere's circular law to this loop, you can see that line integral closed path B dot dl is equal to mu 0 I, because I is the current that is traveling through this loop. Therefore, line integral B dot dl is equal to mu 0 I. Consider another Amperian loop which is stretched so that it encloses the left side of the capacitor. When you apply Ampere's circular law, we can see that line integral B dot dl equal to 0. Because this surface is not enclosing any current, therefore line integral B dot dl is equal to 0. So this law is not valid between the plates of a parallel plate capacitor. Maxwell removed the problem of current continuity and inconsistency in Ampere's circular law by introducing the concept of displacement current. There is a current flow between the plates of the capacitor. This current is termed as the displacement current, which is arising due to the change in electric flux with time. Now we can derive the expression for the displacement current. The electric field that exists between the plates of the capacitor E equal to sigma by epsilon 0. The sigma is the surface charge density, which is nothing but Q by A. So electric field can be expressed as Q by A epsilon 0. The flux linked with the surface phi E equal to E into A equal to Q by epsilon 0. Therefore, the rate of change of flux with time, that is d by dt of phi E, is equal to 1 by epsilon 0 dq by dt, or epsilon 0 d by dt of phi E is equal to dq by dt, where dq by dt is the current. So displacement current is given by epsilon 0 d by dt of phi E, or it can also be expressed as epsilon 0 a d by dt of E. So two types of current flow through a circuit: conduction current and displacement current. In region 1, the current that flow is called conduction current, and region 2, the current that flow is called the displacement current. Therefore, the modified Ampere's circular law is line integral closed path B dot dl is equal to mu 0 I plus mu 0 epsilon 0 d by dt of phi, where I is called the conduction current and epsilon 0 d by dt of phi E is called the displacement current. Expression for conduction current density and displacement current density. Conduction current Jc is equal to Ic divided by A. According to Ohm's law, V equal to IR. Ic can be written as V by R. Therefore, the conduction current density is equal to V divided by RA. But R equal to L rho by A. Substituting the value of R and cancelling A, we get V divided by rho L. But E equal to V by L and sigma equal to 1 by rho. Therefore, the expression for current density becomes sigma E. Displacement current density JD is equal to ID divided by A. Displacement current is equal to epsilon 0 A dou by dou T of E. Substituting the value of ID, we get JD is equal to epsilon 0 dou E by dou T, or JD equal to dou by dou T of D. Comparison between conduction current and displacement current. Conduction current obeys Ohm's law. Displacement current does not obey Ohm's law. Conduction current is the actual current, whereas displacement current is the apparent current produced by the time-varying electric field. Conduction current density is represented by J equal to sigma E, and displacement current density is represented by J equal to dou by dou T of D. Equation of continuity. Consider a charge inside a volume bound by S, and Q in represents the net charge inside the volume. Let there be a current flow out of the region. We know current I equal to dq by dt, and the corresponding current density J is equal to I by A. Take a small area ds on the surface. The current through this elementary area is given by di is equal to J dot ds. Therefore, the total current which is flowing out of the entire region can be obtained by the following equation, that is I is equal to surface integral closed part J dot ds. So due to the current flow, there will be a decreasing charge within the volume. We know current is due to the movement of charge. Therefore, we can write surface integral J dot ds, that is a current flowing out of the surface, equal to decreasing charge within the volume, which is given by minus dou q by dou t. The total charge inside the volume q equal to integral v rho dv, where rho is the volume charge density. Therefore, we can write surface integral J dot ds is equal to minus dou by dou t of volume integral v rho dv. Applying Gauss divergence theorem, converting the surface integral to volume integral, we get volume integral del dot j dv is equal to minus dou by dou t of volume integral v rho dv, or del dot j is equal to minus dou by dou t of rho. That is, the rate of decrease of charge within a closed volume equals the net rate of flow of charge out of the volume, or rate of increase of charge within a closed volume equals the net rate of flow of charge into the volume, which is called the equation of continuity.